What we have seen in the previous example is typical of linear recurrence relations with constant coefficients. Um, I'm referring to the fact that the generating function turned out to be a rational function. And this is not a coincidence because, well, we can prove that for a linear homogeneous recurrence relation of degree k with constant coefficients, the generating function of the sequence is always a rational function. And it's simply demonstrated here. You can just write the general case. This is the homogeneous case, and it's easy to prove this result with the homogeneous case. But we'll also later on see that if you have the homogeneous solution, but the recurrence relation is a non-homogeneous one, you can also use the homogeneous solution as part of your solution. We are going to see how that is done when we talk about the characteristic equation. But for the time being, let's focus on the homogeneous case. So Tn equals C1 Tn minus 1 plus C2 Tn minus 2 plus dot 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 up to Ck Tn minus k. So this is the general case for linear, homogeneous, constant coefficient recurrence relation with degree k. Now again, apply the same approach, multiply both sides of the equality by x to power n, and sum both sides from n equals k up to infinity. Now this case, in the example, we started from 1. Here we have to start from k because the smallest index is n minus k, and that should be 0. So start the index from n equals k up to infinity. And again, the term on the left-hand side is going to be equal to the characteristic function if the sum started from 0. Therefore, if I subtract these terms from 0 up to k minus 1, I get the left-hand side. So this is equal to the characteristic function minus Tn x to power n summed up from n equals 0 to k minus 1. And apply the same approach for all the terms here. You see this one, n starts from k, but you see the index starts from n minus 1. So it starts from k minus 1. Therefore, I'm going to subtract the terms up to k minus 2. But I also have an x here because you see t has the index n minus 1, but x has the exponent of n. Okay, therefore, if you make this n minus 1 and pull one of the x's out, this is what you get. Similarly, make this n minus 2 and put x squared here, which appears here. Okay, so the approach is exactly the same. And then what you do is you put this term to the right-hand side and pull all the f of x terms to the left-hand side, and then solve for f of x, and this is what you get. Okay, all these terms, this term multiplied by, of course, c1 times x, and this term multiplied by c2 times x squared, etc. This is what you get. In another way, you can express this in this way, and in the denominator here we have, because 1 comes from this term, and then you have c1x times f of x, and then c2 times x squared times f of x, c3 times x cubed f of x, etc. So they all appear in this term, minus c2x squared dot dot dot, which becomes the denominator. Okay, and that I can simply write as this sum. So this here, when you look at this, this is definitely a rational function. And why is this important? Because you can always apply partial fraction expansion to a rational function. Okay, you have to factor out the polynomial factors of this expression in the denominator, and then write them as a sum of ratios of polynomials. And then what you obtain is going to be easy to express in a sum that will give you an easy way to write the coefficient of the x to the power n term in the generating function.